really. So next up, we've got Dr. Michael Jack from Otago University. Going to be talking about seasonal demand and near zero energy buildings. Is the mouse going? You can see notes. Yeah.
Hey, kia ora koutou, everyone. My name's Michael Jack. So I guess most of my work is thinking about the energy system of New Zealand, and this is work we did focusing on the built environment, which is not really my specialty, but I think this hopefully this will be interesting to you. So most of this work was carried out by Hannah Connings, a master's student. Don't know what's happened with the font, but. Okay, so let me start with the problem to kind of introduce this topic. So 75% of our emissions are energy related, and a lot of those have nothing to do with buildings. So we've got a lot of industry, we've got a lot of transportation emissions. And kind of that's the bigger picture. And there's been a solution that's been proposed by a number of people, and it's kind of electrify everything is the simplistic way of thinking about it. And I don't know exactly when it kind of rose to prominence, but for me it was this 2012 paper that kind of pointed out that if you really want to reduce emissions to do deep reductions in emissions, you need to start thinking about electrification. So, I mean, I like to think of it as like a three-step plan, and a number of people have talked about this in the past. That the first point is increase efficiency. That's really important. Then you need to think about increasing the amount of renewable electricity you have, and then you electrify everything. And the reason I really like this kind of solution is it aligns with where we're heading with technology. So technology costs are going down in renewable electricity generation. It aligns with thermodynamics. So this fits with my physicist brain. We really want efficiency, and electrifying transport and heat makes a lot of sense from an efficiency perspective. So there's a bunch of challenges, obviously, with this problem, and there's things like the sheer size of the change required, and as the last speaker said, huge investment required in making these changes, and we need sustainable finance, we need political will. There are the hard to abate sectors like heavy transport, aviation, steelmaking. Okay, but the problem I want to talk about, and this was also talked about by Lloyd in his talk, is the mismatch, the timing mismatch between variable renewable supply and demand. So this is shown in this picture here in a daily scale, but energy demand varies on a range of timescales from days, sort of minutes, hours, days to seasons. And that's the same with renewable resources. They vary on these timescales as well. And often they don't match. And that's the issue. And if you have a small, if you have a timescale where you're just talking about days, then we know how to solve that. We can solve that with battery storage. We can solve that with demand response, demand flexibility. But then how do you start solving this type of problem when your mismatch extends to seasons? That's one of the real issues. And in New Zealand, we already have started thinking about this because we're so highly renewable at the moment. We're thinking about, okay, what if we get to 90%? What if we get to 95%? What if we get to 100%? And one of the main issues we can see already is that peak in winter demand. Okay, and one way of sort of quantifying that is thinking about what's the size of the energy we'd have to store to meet that demand. And there's been a number of sort of supply side solutions been proposed to this problem. Overbuild is one of them. This is where you essentially build renewables so that you can basically waste some of the renewables when you don't need them. You overbuild everything. One of the other ones, of course, you've heard a lot about is this big battery project, which is this idea of a very large pumped hydro scheme where we can store essentially that peak of demand so that we can survive a dry period. When we don't have very much hydro, we don't have very much wind. Okay, but all these proposed solutions come at a very huge cost, and the thing is, whenever you have a problem like this, you don't just think about supply side solutions. You have to think about what's the possibility on the demand side, and of course, all of you know here that it's residential electricity heating demand that drives that winter peak. Around about 70% of that winter peak is driven simply by residential heating. So, I mean, our project is really about going, okay, so what are the options on the demand side to kind of think about how you might deal with this problem? And of course, we have to think about the context of housing in New Zealand and the fact that we know that we have poor housing conditions and that they have a huge impact on health. So energy efficiency or better housing makes a whole lot of sense anyway, right? I don't need to convince you of that. So all I'm talking about here is the seasonal variability aspects. You build efficient, warm houses for health reasons. This is what I'm talking about here is just an extra thing that could provide a benefit. So what we wanted to explore was what would the impact be of large-scale uptake of very efficient houses, like passive houses that we're talking about here. What impact would that have on winter peak? So quantifying that. And then there's a lot of talk, especially in Europe, about moving beyond that, that nearly zero energy house and going to net zero housing, because that's a whole different ball game again. That's saying, okay, let's now generate. And when you're thinking about solar generation, that's got a seasonal component. So what does that do to the seasonal impact we're talking about? So just a quick aside, we always in New Zealand, we always ignore the greenhouse gas emissions, or at least the operational emissions from housing. We think it's quite a small component, but it's actually the third largest emission after transport and industrial heat in New Zealand. So yeah, it's kind of I think an area that's sort of not thought of very much, and this is because we use about 25% natural gas for our heating and about the same for hot water heating. So this is just some recent work we did to try and break down those emissions across the country, because if you look at, say, ECA numbers, they have one number for the whole country for space heating. And so we wanted to look at that a little bit more detail. And the results show that population is not a very good estimate of how much heating demand you need and your greenhouse gas emissions, which is kind of not surprising. So this is just another picture of these emissions. So if you're interested in this, we're working on this topic. Okay, so back to the main thing that I wanted to talk about. So what we tried to do was to come up with these scenarios for future buildings. So we developed this housing stock model and wanted to look at new houses, but also an aggressive retrofit scheme. So that's kind of what's shown in this graph here. We wanted to look at different scenarios for building efficiency standards. So the normal building code, but also basically the state-of-the-art, the passive house type standard. We looked at multiple climate zones across New Zealand as part of that. And we also wanted to look at self-generation, as I said before. So this is just showing you how that solar variation looks across New Zealand. So the methodology we use, so we're very, we don't do proper building modeling like we've heard in a number of talks today, where people have actually done careful modeling of buildings. We do a very broad brush approach. So we use this approach, which is kind of a monthly calculation procedure, and apply it to all these houses. So we're not doing detailed modeling on individual houses or anything clever like that. This is just a broad brush approach to give to kind of get an order of magnitude numbers. One of the so we assume electric heating, electrified heating, because that's kind of where things are heading. We also assume that the buildings that are newly built and are retrofitted are heated to healthy temperatures. We chose 18 degrees for this work. We looked at the heating and the cooling that we're exploring. We wanted to take into account temperature-dependent coefficients of performance for those buildings. Just, I guess, with the argument that, okay, why don't we just go to really efficient heat pumps? That'll solve the problem. So we wanted to explore that. We looked at, so this is just a picture of how solar generation changes as you change tilt and orientation. So let's see if this can work. So that plus there is the, so this is a number of different locations across New Zealand. That plus there gives you the greatest amount of solar generation, and the circle gives you the minimum of the seasonal variation. So we wanted to have a look at kind of what happens with tilt angle, as you know, with this solar generation. You know, tilt angles is going to have an effect on this variation, and we wanted to have a look at it as well. It's interesting to note that actually orientation doesn't have a very large effect on solar generation. And because we didn't really know the orientation of these solar panels on people's roofs, we just averaged from -45 to 45 degrees to explore that. So these are kind of the scenarios we looked at. We looked at the current building code, and we looked at a very high performance standard, which is basically the passive house standard. We also looked at a range of scenarios for solar PV penetration. And so that first factor there is just a kind of how many solar panels we're talking about. And our highest scenario was basically 50% of houses had a kind of an 8 kilowatt type system on its roof. And the other scenario was about 1/3 of that. We also looked at really steep tilt angles, 60 degrees versus 30 degrees, to kind of explore that. So here are the results. So this is the result for the annual generation. So we have a base load generation that we assumed we didn't change. So of course that's going to change. We really don't know what's going to happen with that. Often people are going to move to electric vehicles. They're going to choose more efficient appliances. We really don't know what's going to happen there, but we kept it as a base load just so that we can compare our results against that. So we're not modeling that. We're just modeling the space heating. So if you look at the building code, no solar. Now we're heating our houses to high temperatures, and we're doing electrification. You know, we're heating them electrically. And so there's that increase in generation as we go out to 2050. If you stay with a very, very high standard, then you basically flatline. You don't get any increase at all in your generation. If you start thinking about adding solar to the system, then these start dipping down. So that's the very high scenario with very high solar. So you're getting you're reducing annual demand. It's really important to have a look at what this means in terms of the new versus retrofit houses. You can't ignore the retrofits in any of these scenarios. The retrofits are really important. The new component actually only is a smaller percentage of these results. Okay, so here are the seasonal results. So just taking you through this green line here, the green dotted line is what we currently have in terms of our seasonal variation. If we don't do anything, if we stick with the current building code without any solar, then we're increasing our peak significantly. We're also increasing this kind of base load that's happening. That's just because we've got more buildings essentially. But there is also a component of cooling that's coming in here that we've modeled. Okay, so we've got a significant increase in our the variation between the minimum and the maximum due to because of those the building code. And then if we move to the passive house standard or the very high standard, which is the kind of the blue triangles, that's kind of halved that in 2050. One thing that's also interesting to look at is to say, okay, what about nearly zero versus net zero? And so this graph here shows you the nearly zero. So this is without self-generation. And then once you put in the self-generation, you're definitely reducing your winter peak because there's still some generation in winter, but you've increased your variation quite significantly. So if I guess we're electrifying everything else will be pushed up, increasing that peak. One other thing that's interesting is just the difference in tilt angle. These two have a slightly different tilt angle. Well, so quite a significant difference in tilt angle, 60 versus 30, but the difference is not that large. Just looking at the results in a different way as a map across New Zealand, these are the annual results. So it's interesting to note that here we've got the very high performance no solar case looks very similar to the building code case with high solar penetration, right? If you're just looking at the annual demand, those diagonals across there. But then when you look at the difference between them in the seasonal perspective, there's quite a difference there. This is the relative variability, which is just the variability in between summer and winter. You can also see there's quite a significant change when you go from the no solar case to the high solar case in terms of variability. And it's quite regionally dependent, which is one thing that's quite interesting. So finally, just to show you some more plots, this is maybe a bit hard to read, but this is kind of as you're moving towards 2050, what happens to the peak and the trough in your demand. Okay, that's what we're trying to plot here. And I'll just bring to your attention some things. It's interesting that in Auckland, the variation between winter and summer actually reduces out to 2050, and that's due to the increase in cooling that we're seeing in our analysis. If you go to the very high scenario, everything reduces, so that seasonal variation reduces in every single location across New Zealand. And in the very high scenario, you actually get that kind of reduction in peak, but the variation increases as a proportion and as you add solar. Yeah, so I guess just to conclude then, what we've tried to do here is quantify the impact of future building policy choices on the annual and seasonal variation in electricity demand. And I guess my takeaway message would be that energy efficient buildings should be the priority in all regions. They reduce both annual and seasonal demand. I guess this might be a little bit controversial, but I guess what I want to say is that the seasonal variation in solar generation is minimized by those steep installation tilts, and Potentially, we need to avoid this large-scale uptake in regions with cold winter temperatures and relatively limited solar resources, so below about 42 degrees south. So I'm not kind of anti-solar in a way. I mean, I think that it has its place, and especially now, when we're in the initial stage of solar adoption, there's no reason to kind of stop doing solar. I guess I'm just saying that there's this large scale issue that's going to come if we kind of specify our buildings need to be net zero or anything like that. Those, I think, start to be problematic or will start to be problematic in the future. There may be other reasons you want to do solar. It may be that the cost of solar becomes so cheap that then it doesn't sort of matter. It may be cheaper than wind, and then it might be a good option.